makes it hard to see.
All right. So just want to see if there's any way that I can see the chat too, but well, if not, let's see. Well, I think for time purposes, I'm going to start.
I was just going to ask, could you make the size of your font bigger?
I will right now. And so yeah, if hello everyone, my name is Naty Clementi. I work for Coil, and I just want to make you aware that you know where I work. And today we're going to be learning a little bit more about Dask, and hopefully this will be sort of like an introductory tutorial that everyone could get to learn more about Dask if you know about pandas and scikit-learn and are familiarized with the Python ecosystem. If you're joining and following along with Binder, you should be able to see a launch Binder button on where the tutorial material is. Click on there, should take 1-2 minutes to load up. And if you're working locally, please start your Jupyter Lab, and then we're gonna go from there. So now I am going to minimize this, make this one bigger. Is that big enough, or can everyone see or read?
Maybe a little bigger.
Yeah, I can only read the headlines, not the main type.
All right. Trying. Let's see. What about now? Is that big enough?
One more, maybe. I feel like some people have might be watching on a very small laptop screen.
Yeah, that might make sense. Okay, I made it one more bigger in there. Hopefully, okay. Can do one more. Maybe there.
Good. Yeah, that's good.
Okay. So I guess like a good point to start, it would be like, if you ever heard about Dask, maybe you have a question on what is it and when you should use it. And these are like fairly common questions. Some people tend to think that, oh, I just want to make my things faster, so I'm going to use Dask, but that's not necessarily the case. So if you might have one of these questions, hopefully along the way, we'll be able to answer some of those, and then you will get a better idea on when and what is Dask, and then when you can use it or you should use it. Today, we're going to go over like some material, but the world of Dask is like fairly big, and luckily it's very well documented. So then you can find documentation on the docs that are already, I mean, they're always online. If you have any bug report or you want a feature request, usually we recommend people to open in an issue on GitHub. If you want to engage with the community, there is a Slack community, but recently, if you have questions about how to use Dask, which probably you might have after this tutorial and you're new to Dask and you want to know how to use it, we encourage people to post these questions on the discourse. There are like different categories there, and then you can see, depends on the problem that you have and how things go, you will get answers from people from the community. So on a nutshell, like what is Dask? So Dask is a flexible library for parallel computing in Python. And the good thing about Dask is that it allows the syntax of the PyData ecosystem. So if you already are working with pandas and scikit-learn and Python, the odds are that Dask syntax will sound very familiar, also with NumPy. So for example, if you're reading a CSV in pandas, the typical way is pandas.read CSV, as in here. The way that that will look like in Dask, it will be something like this. And we will go over what this asterisk means afterwards, because, but the idea is that here the syntax is fairly the same, similar with the group by, and there are a couple of things that are different. You will see this dot compute more often, And hopefully all this, if you have any questions about that, they will be clarified along the way. So since they're all family, basically pandas and Dask and scikit-learn and all the Python world, then this, hopefully, not always, it will allow that you can scale your existing workflows with a small amount of changes. So going from a pandas kind of workflow to a Dask workflow, hopefully wouldn't be, or in most cases wouldn't be that painful to adapt. While in other languages, you might need to rewrite the whole code. So that's the main point about Dask, is that it will enable you to accelerate computations and perform some computations that just don't fit in memory. So if things work in your laptop, it will also scale out of larger clusters. And most of the times, the advantage of using Dask is that you will also get a dashboard and diagnostic tools that we'll explore today. So a little bit of how Dask is sort of like built. So we have multiple collections. So Dask Array is similar towards the NumPy API. Dask DataFrame is related to pandas. We have also Dask Bag, Dask Delayed, and Futures. And the way this works is we create, or Dask creates task graphs that the schedulers will execute those task graphs. And then we'll see what all this means, but more or less, this is how Dask works under the hood. So a little bit of jargon. You will hear whenever we're talking in the Dask world about the client, the scheduler, and the workers. So the client is the user entry point for cluster users. So in other words, the client is where the Python code lives, and it communicates to the scheduler, which they will pass along the task to be executed. So for example, for me here, the client will be my laptop, and it just happens to be that the scheduler and the workers will also be my laptop. But if you're working on a cluster, that might not be the case. So the scheduler is the task manager. So it sends the task to the workers, and the workers are the ones that compute the tasks. So more or less, this looks kind of like this. So the client will be where your Python script, your Jupyter notebooks are, and then the scheduler is the one that's going to be sending the tasks to the workers to be computed. So when do we use Dask? And when can we say that this could be useful, or how can you identify this is useful for your workflow? So there's not a straight answer to this, but overall, we have some rule of thumbs on when you should or you should not use Dask. So for example, if your data fits in memory, meaning fits in RAM, you don't have a big amount of data, your data fits in RAM, then you want to stick to pandas and NumPy. They're very well optimized, and Dask might be able to help, but usually is not the case. Now, if your computations take forever, even though they fit in memory, then Dask might be able to help. And if your computations don't take forever and they don't fit in, and they do fit properly in memory, then that's awesome. You don't have a problem, then you shouldn't be looking for a solution. And another thing to look for is if you have what we call embarrassingly parallelizable code, which is sometimes certain for loops that we have or certain type of codes. We'll see some examples, should be easy to parallelize. And in that case, Dask can help. If you're not sure how these examples look like, we have a link over here. And then you can take a look and see if your code looks like that. If your code is super complicated and it doesn't look easy to parallelize, it might be hard that just to try to use Dask will solve your problems. So in more of in a graphic way, if we have this plot, which it might be a little bit hard to see on the shape, but if your data size fits in RAM and your model kind of problems, so if you're on this, in this part, oops, what happens? It just executed the cell. So coming back, if you if your problems fit in RAM and they don't take too long to compute and you live in this bottom left corner, then you're in a happy place. You probably don't need Dask. If you're anywhere else, Dask is probably fair game. And then how complicated things can get, it will depend on your problem. But that could be a good use case. So sort of as a disclaimer, like when we say Dask might be able to help, it's because you should try to accelerate your code with NumPy or Numba, check-in types using your data frames. And then if those things are not helping, then you might consider using Dask. And even with large data sets, like not always Dask will make your life easier. This is just a sort of like short overview on when you should or not use Dask. There are plenty of material to read about what are best practices for arrays, for data frames, how you can accelerate your code. We always encourage you to go and read the documentation and then use the resources available like this course or GitHub to ask more questions. Some people may ask why using Dask and not other things to parallelize your code. I would say that one of the biggest advantages, if your workflow is already in Python and you live on the PyData ecosystem, then Dask will sound familiar. And it's very encouraged to go this way instead of rewriting your code to adapt to a new language. There are many other reasons why you could use Dask. It will depend on your problem and why you should use it or not. That also could depend on your problem. So we're going to get now into some code. But if you, this is a short version of a tutorial. If you want to do a more extensive tutorial, there is a Dask tutorial available on GitHub. And there are some Dask trainings. For example, Cole gave some Dask trainings. If that's something that you're interested in, that it's a couple of days and stuff, you could check this link. If someone is interested in that, I believe that there is some sort of like 50% discount code running. I can look into that at the end. But for now, let's just dive into some code and let's get our hands on. So if you are in, I probably forgot to mention this, if you were in Binder or locally, you can check on the notebooks. And we're going to move now to the one that's called delay. So, all right, I'm going to close this one. Well, not that one. And let's minimize this so we can see. So one of the first things that you might want to do when you're like diving into see if you could use Dask or not is you already have existing code that works. How can I try to make that run in parallel? For that, a first step that we could do is like try to use Dask Delayed. So to do that, like you want to try to identify if there is some level of parallelism that you could exploit with Dask Delayed. So I'm going to show you now like a simple example where that is sort of obvious. Unluckily, this is not the way that it happens all the time in our workdays, but it's just to give you an idea how things work. So for example, if we have, let's say these two functions that increments the value of a number by 1 and another one that adds 2 numbers. Here we're using this sleep here is just to delay things 1 second to sort of simulate some kind of work. So this function, nothing new here, things run in serial. So we just run that. Well, we're not running anything, we just define the functions. Now, if I run these functions, let's see how long it takes. We should. Okay, so we see this takes 3 seconds, which I would expect. So we have one call of inc here, which is basically the time that this is taking here. We call it again. So that will be another second. And then we call add at the end. So that will be another second. Excuse me. So if we think about this workflow, you could think of in this sort of graph. So we have 2 calls of inc, which are the circles over here. And once I get those results, I gather those results, and then I call add, and then I get the output. So if you see here, this call to inc, the top one and the bottom one are independent, and we could run them in parallel. So let's see how we would do that. To do that, we can use one of the Dask collections called Delayed. So we import that from Dask. And Dask Delayed works as a decorator. So we decorate the function. Like if you see here, we're decorating or sort of like passing a function inside a function, if you want to think it that way. And then we provide the argument. And let's see how long this takes. So we run this. And you'll see that here, it's like super, super, super fast. Well, what happened here is like, up to this moment, we haven't computed anything yet. So when we call the delay version of the functions, the original function is not actually called yet, as we said. So if we want to inspect what C looks like, so we see here, we say that this is a delay add, and then it has a bunch of numbers. So this is sort of an object, but we can visualize this. So if we hit on visualize, so you'll see that this graph or task graph looks like the one that we were thinking before. So this is sort of setting up how the computations will be run. And now let's see how we actually compute them. So to do that, we call compute. So this is sort of like one difference that we have with normal running of things. So we run this, and this takes 2 seconds. So the reason why it takes 2 seconds is because the 2 increments run in parallel, so they take like 1 second each. Both of them take 1 second. And then we have the other second from the add computation. So we've done our first in parallel computation. Now, if you are running things on Binder, you might notice that this wall time actually says 3 seconds. The reason why that happens is because by default, Binder will give you only 1 worker with 1 thread. So we cannot parallelize things. There is a way of fixing sort of that in Binder. You can copy this code that is over here and run this cell again. Don't worry about what this code means right now. We will go over it in the next notebook. But for now, if you want to see that effect of things going a little bit faster, please just copy and paste this cell, and then you can run it. So let's see a little bit, one example that is a little bit more complicated. So now let's create some data. So 8 numbers from 1 to 8. And now here we have some sequential code where what we're doing is with each element of this data, we're like grabbing one element, incrementing it by 1 with this function. We are appending the result to this list, the results list. And then at the end, we are summing all of the results. So if we have a length of data 8, I would expect this to take about 8 seconds because we have 8 calls of the increment function. So as we mentioned, 8 seconds, then we can get here the total. Here, nothing is in parallel. But all of this increments call can be done in parallel. So let's see how do we adapt the code to do this. So we can do a delay thing over here, but then we also need to tell this sum function to sort of wait kind of for all these computations. So the way that we do that, this is an exercise, but we're just going to do it together and see it together. Here, we just wrap the increment function, same way that we did before. And now what we do is we tell the sum, delay sum, so then it will gather all the elements that we had before and then sum them. So up to now, we haven't done any computation. Remember that up to here, whenever we apply the delay decorator, things are still on the graph kind of look. So the way that the graph will look in this case is we have all the increment calls in parallel, and then they all go to the sum, and then we get the final result. So let's compute it and see how long it takes. Great, so I expected it takes only 1 second because the 8 computations here run in parallel. The reason why it's taking 1 second is because I have 8 threads on my machine. If you were to have less threads, then this will take, let's say that you have 4 threads, this will take 2 seconds because first it runs 4 and then it runs the next 4. So that will depend on what you have available in your machine, but that's the idea. So here you can check how many threads are available, or like cores are available on your machine. So another way of using the delay decorator is by having this sort of like nice syntax over here. And what this does is it already converts this function into a delayed kind of function. So let's see how that works. If I decorate the double function in this way, now if I try to call double of 4, this is already a delayed object. So that could be useful. So one thing that we could do is the functions that we have before, we can decorate them using the delay, this nice delay syntax, and then we can use it right away in some code. The delayed objects support several standard Python operations. So if you want to do multiplications and sums or slicing, these things already, the delay decorator will take care of it. So for example, in this case, these inc functions now are the ones that are decorated with the delayed nice syntax over here. So all of these guys are delayed objects. So when if we try to do this computation, result should look like in a graph way. So we'll just visualize this. Oh, I didn't run this one. There we go. So now you can see that we have multiple inc calls. So those are here. And then it's grabbing. So we have all this in parallel, and then it's doing this sort of multiplications here. And this last plus is this add. So let's see how long this takes. 1 second, because again, like we had eight threads available. So all these inc computations are running in parallel. And these ones are Python computations. So we are like doing the multiplication of 2 numbers and then sum them. So this takes, I don't know, milliseconds or microseconds compared. So that's why we don't see them in here. That's probably the 0.1 second accumulated. So another example.
Sorry, it takes like typically about 1 millisecond to schedule each individual task.
Awesome.
So as long as like the actual work that we want to do is like a fair bit longer than that, then it's pretty negligible, which is nice.
Yeah.
So it's like 1 second actually doing work is like a really great length.
Awesome. Thanks for that. I did not know that. So another example where we could see this decorated functions with delayed in action is similar to the for loop that we had before. So we have data, but notice now here this inc, double, and add are already the parallel versions. So when we run this, you'll see this totally a delay object. So we can visualize this. It's going to get a little bit bigger, the graph. And this can get very, very, very big and complicated if we do more complicated computations. But you see here that double and inc are running sort of in parallel. And we have 8. So we have 8 times 2 will be 16. So there should be 8 inks and 8 doubles. So then these are the ones that we see here. And then we just have these ads. That these ads are now the ones that they are actually the decorated version. So if we run this, takes about, say, 4 seconds.
Very
So,
nice. Naty, there's a really interesting question that's popped up in the chat, and I feel like other people might be wondering it as well. So the question is about what's the difference between the wall time here versus the total time that's being reported? And so the answer that we've just given in the chat that everybody else might like to hear as well is that the wall time is the total time in real time, like your experience, whereas this total is effectively like double counting a lot of the time, because we have a lot of parallel operations happening. It's counting the total time for each of those, even though they're running simultaneously. So that's why this like the wall time is sort of the effective experience.
Yeah. I wonder if, do we have any documentation about this on Dask? I bet there might be something where it reports which of this one it is.
I think so, although actually now that I'm looking at the total time here, this is in milliseconds rather than seconds. So perhaps this total is actually counting something different than what I've expected it to be. I know that the wall time is definitely the actual
weight.
Yeah,
I think this total might be the sum between
the system,
user and system. Because it seems so, but I do not remember what is user and system. CPU times what actually are computing.
Yeah, it's the wall time that we care about.
Yep. In terms of how long you will actually wait for the computations, say you have something super big, you will be looking at the wall time. It's like, since it started and it finished. But we can look into that. I think that's a great question. And definitely I will take some notes on that. Or if someone, maybe Sarah, can you take some notes on that? And then we'll add it to the tutorial to have that, that added. Thanks for the question. So there are plenty of things to learn about delay. Delay can be very, very useful. This is just like a rough overview about it. I added here a bunch of like different lessons, other PyData global tutorials that explain delayed and have way more examples. And there's documentation and best practices too. But for now, we can move to, let's see, what the schedulers are. Because so far, we haven't mentioned the schedulers beyond the overview and the introduction. And we haven't like seen actually clients and workers and things over here. So for now, it's like, this is just sort of using what it's under the hood in your machine. So where are the schedulers? So we said like, so far, we only seen like the power of Dask Delayed, and we got familiarized with the idea of what a task graph is, and we learned that this task graph need to be executed. But who does that, and who is the one that actually send this task to be executed? So that one is the scheduler. So you can think of the scheduler, this sort of, this is a big task graph, and it's always like a nice example to see how complicated things can get. Where you would say that probably the coloring part is like sort of what the scheduler is saying, like, hey, here you go, do this, do that. And the thing about schedulers is there are different task schedulers in Dask, and sometimes you will use one or the other, or the others, depends on what's your situation. So like on a very high level, we have two different kind of schedulers, what is called the single machine scheduler and the distributed schedulers. So single machine schedulers require like no setup, as we saw before, like in we were just like importing Dask and then doing Dask.delay, and suddenly things were happening and running faster. So they only use the Python standard library, and they provide a basic feature on a local processor thread pool. And the single machine schedulers have like sort of three types of schedulers. which are the one that is based on threads. So this one is the one by default. There's one that's set up by default. So the thread scheduler will execute computations with what's called the concurrent future thread pool executor. And that's like a lot of words. For now, don't worry about it. But it's the default for Dask arrays, DataFrames, and delays. So before, under the hood, whenever we're doing Dask delays, we were using the thread pool executor. Then we have the processes. So this is like a different kind of scheduler. Sorry about the noise. It's overall like we have the processes. So it's the multi-processing scheduler, which executes computations with the process pool executor. Again, another complicated word. For now, just don't worry about it. But this one is a default for what it's called Dask-Bag. In this tutorial, we're not going to get into what Dask-Bag is, as it's a little bit more of a, I would say, an advanced feature, or it's not that commonly used. But if you're interested in knowing what Dask-Bags are, think of bags are probably the parallel versions of lists. And you can read about that in the tutorials, the main Dask tutorials, and then there are other places that if you Google Dask-Bag, you will land into a bunch of documentation. And then we have a single-threaded scheduler. And you might wonder, why would you have a single-threaded scheduler when we're trying to do things in parallel? Well, the reason why is because this can be very useful when debugging. Like when you are trying to debug things in parallel, it can be a little bit complicated. So sometimes you might want to use a single-threaded scheduler. And let's see how these different ones work and sort of how they impact the times of some computations. So same as before, we are importing Dask, delay. We have our beloved inc function, where we still have 1 second of here to simulate some work. This will be the parallel version. So if we run the same for loop example, so you'll see that you have here this delay, and so far nothing has happened. So we have total, as you see here, we have our delay object. And let's see, this is not new, but this is a way of configuring which scheduler you want to use. So let's just for now use the default one, and then we'll change it and see how this works. So you can do with the syntax, configure which one is the scheduler you want to use, and then perform your computation. So if we keep the one that is the default, which is threads, we'll run this, and it will run in 1 second, as we saw before. So nothing too new for now. You can actually also provide what's the number of workers you want to use. So in this case will be 4 threads. So I would expect this now to take double the time, because we have 8 different computations calls here due to that my data is the length of 8. And when we run this, we'll see that this takes actually 2 seconds and a little bit more of time, but it's like the compute time is 2 seconds. So now let's try to use this multi-process scheduler. So we just change it to processes, and we'll see that this takes a little bit more. So it is faster than 8 seconds, but it's not actually 8 seconds. And here I am using the processes scheduler to show you how to use it. But because we are working with delayed objects, like we want to use the threaded one. There is plenty of documentations about when you might want to use one or the other. I put some links at the end of at the beginning and at the end of this notebook. I am trying to think now. I think a good case of use of process will be if you are working with JSON files, and I cannot remember on the top of my head other cases, but in certain situations, this will be useful, and it will be what performs better for you. If you're using bags, Dask bags, that would also work there. And if we use a single threaded scheduler, I would expect this to take as long as the serial version because it's single threaded. So we're going to run it, but for now, you can check that this will take 8 seconds. So these are like the single threaded, the single machine schedulers, but we also have what's called the distributed scheduler. So the Dask distributed scheduler, despite having, oh, there's a typo here. Despite having the distributed word on its name, it also works on single machine. And in general, we would recommend you using the distributed scheduler because it offers features and diagnostics, and you can think of this scheduler as a more advanced scheduler. So you'll see how we'll see now like the advantage of having the diagnosis tool. So this distributed scheduler also as well, you can use it locally, but then also you can use it on remote clusters. Dask clusters involve additional setup that you can read a lot about how to set up your own Dask cluster, and there's plenty of documentation. It's a little bit advanced, so I wouldn't recommend that going in this way, but you're more than welcome to check that documentation. Alternatively, there are some different cloud providers like Coil. There is another one called Saturn Cloud, and other cloud providers that will do all this heavy lifting for you, and you can just see how all the setup is done. We will probably see a little bit at the end of how Coil works, and you can see how easy it will be to spin up a cluster in the cloud. But for now, let's see what this distributed scheduler will do for us. So we imported as from Dask distributed import client. So we need to actually set up the client object that we talked about before. And this is what it will interact with the cluster and the local status and processor in your machine. So now we have it. We got the client. We need to create this client. So we're going to request for like 4 workers. Currently, I'm running things on my machine. So if I do 4 workers, if you're running on Binder, this will probably give you, I believe that this will also give you 4 workers. Here you can see more information about the cluster. You can display this nice wrapper, and you can keep, looking at. So this machine, it's sort of like a cluster on my laptop. Let's put it this way. We have 4 workers, but I'm seeing that I have these 8 threads. I have a total memory of 16 gigabytes. And here is this link to the dashboard. So this is something that we encourage people using. You can click on this and it will show you this. I am using currently I am in Jupyter Lab. So, what happened here? So in Jupyter Lab, you will have this Dask extension if you install things the way that we set up. So here you can actually click on there, and then we'll see this should be here. For some reason, it didn't pick it up, but I believe that if you copy,
I think if you click like the little magnifying glass icon, it tries to refresh.
Awesome.
Yeah.
That's awesome. I didn't know that.
Yeah, usually I think it does refresh by itself within a second or so, but yeah, I have to just click that if I'm impatient.
Yeah, sounds good. So here there are many plots. Some of these plots and visualizations are the ones that are in the dashboard, other ones some extra. But for now, we're going to take a look at, if you click on here, let's see which one is the task stream. So you can actually put it on the side. Then we can get the progress. So the nice things about Jupyter Lab is you can accommodate this the way you want. You can have something useful to look at in general is the workers memory. So we'll have this. Let's see, we can do something like that. Oops. I'm going to make this one smaller probably. And you can also look at the memory of the cluster for purposes of for the purpose of space, I'm going to avoid that one. But we have another one that is very useful is, I think it's called, what is it? M processing, which tells me how many tasks are being processed per worker. So we'll see some action happening in here right now, hopefully. Let's see, I'm maybe making this one a little bit smaller. So let's see something happening here. So we have the client now, and then we have these nice visualizations. And let's see what happened now when we do the total compute of the computations that we have here, the graph that we set up all the way up here. So total compute, and we'll see some things happening. Okay, this was very fast. We'll see some that take a little bit longer, but here you'll see that, and this is like a little bit blown up by the Dask application, but you have the memory of the workers. So each worker has its own bar. So you can see there is details about what is processed, memory, manage, and manage. That's a little bit maybe too advanced for now, but there is plenty of links on reading information about the memory. The important thing, or the thing that I like to look a lot, is the task stream. So you'll see that there are like 8 sort of like lines. So that is 1 per thread. And you see this, like each of these lines are the ink computation. And there's something going on in here that is, oh, transfer all this ones to the sum. And then you get to see how this goes. These are the individual tasks.
Naty, is that
Yep.
8 because you have 8 cores on your machine? Is that what you said earlier, rather than 8
Yes.
threads? Yeah.
So when we check in here, it says I have 4 workers, but I have a total of 8 threads.
Excellent.
So
there's
each
a question
worker
in the chat, about exactly this, and they'd like just to clarify like the difference between the number of workers and the number of threads.
Yeah, absolutely. So in general, like imagine that. So sometimes you have certain machines that it's like one physical, I would say core is called, not sure if that's the right word. But it can run in multi-thread stage. So if you check, I would say like, it depends on the machines. So sometimes you can run only single thread. So if that's one case, then you will only see 4 workers and 4 threads. So in here, you will be seeing only 4. There are other machines that sometimes you can have more than 2 threads per worker. That's usually related to how the hardware it's specified, I believe. I'm not sure if there is anything beyond that. Maybe, do you have anything else to add, Genevieve? I don't remember more than that.
I've just, maybe I'll pop a link to a particular Stack Overflow question that seems like very related to the question we already have in the chat, where it's from a few years ago. Matt's just tried to clarify in it that by default, Dask creates a single process with as many threads as you have logical cores on your machine. So if we're just working on a laptop like Naty is now, then the Dask sort of has a look at what's available, and if Naty was going to check herself and look at like multiprocessing the CPU count, then typically you get like the same number of Dask workers, 1 for each, and that could have like, I think typically like you get 2 threads.
2 threads.
Those, but that's more of a hardware sort of level.
Yeah, I think, remember back, well, maybe if you're too young, you might not, but remember back in the day when the Intel dual core was sort of released, it was like, that you could actually have that multi-thread situation. So it was like, oh, well, I have one machine or one CPU, but actually can run 2 things at the same time.
Yeah, so I think because it's the default, probably like the number of workers and the number of cores are generally the same. Although I think if you tried to dig around in the settings, you could maybe change that to be something different. But Dask is kind of smart, so it'll pick something sensible for you, and that tends to be like 1 worker per core. And those cores, because of these sort of very fancy hardware innovations, like have multiple threads in them.
It's good. Yeah, it's always it can get as tricky as you want, but yeah. So moving on, like another task collection that we could say was called the futures interface, and this is another way of sort of like being able to exploit the code that you already have in work. So let's see how we can use this. So this sort of exploits on the back what are called the Python concurrent futures, and it provides a finer control on asynchronous computations. So we have the function, our inc function, not delay the creator, anything in here yet. You can, if we run this locally, serial code, so you won't see any activity on the dashboard. We get 2, this took about 1 second. And one way that we could actually tell the client to run this computation is by submitting this function with its respective parameter. But in this case, it will be, if you see here, when we run it, it'll say that it's pending. So it's kind of running on the back, but your execution on the notebook is already there. I wanted to see, this is like not great to see, but here you see, I'll probably check on the dashboard later on, but if you see here, it says inc. This will show us the progress of the specific type of tasks that are running. So the color matches with what is on the task string. So far, like we submitted that, and you see the status pending, but you saw some movement, but your client or like the notebook was sort of released faster. So here now it says it's finished. And if we want to check what the result is, we just do future result. So we get that too. So now you might wonder, okay, but if I want to do this for a for loop, then I have to do like bunch of submits multiple times. But luckily, there is the client map function for running a function across an iterable of inputs. So if we could do that for loop that we had before that we run, and then we use the delay decorator, we can use the futures instance to sort of map each of the inc calls to the data that we had before. So in here, we will be running inc for each of the values of this list. So if you see here, some things are happening on the back, and we have all this pending. If you notice, there is one that was all finished, it's because it remembers the one that we just did. And if we want to gather the results, you could do a less comprehension, sort of for loop, and then trying to get all these features, or you can use the client gather function and grab these results. So one thing that you can do with futures, since they obey what is called the Python garbage collection, you can delete things, you can remove things, and if you don't, then the data of the futures will still point to live in the Dask worker until there are no more references to that future. So if you think that you're not going to use these features anymore, or one of these ones anymore, you can actually delete it. If you don't, as you saw here, that we have one that was already finished, that was the one that we computed before. So it still had that reference to that future. So as you see, and then if you delete one, you will see that now you have 7. So all the other ones that you haven't deleted, they are still living in there. One small sort of exercise that we could do, or I can show you like how we got about this. If you want to do it afterwards, feel free to do it too. let's say that we have 3 new functions. Now we're doing a sleep of 0.5 instead of 1 second. And I want to parallelize this kind of code. Now we have it in range 10. So then we will have like 10 different calls for each of these ones over here. So how we would write this in, this will take a couple seconds, actually. I should have timed it. But it will take a bit. And the way that we will actually run this, and then using the futures interface, will be using client submit. So let's see how we can time this. But well, it wouldn't make that much sense to time, since this cell will get executed, but things will be running on the back. So let's see how that works. So if I execute this cell, so you'll see that things are like running over here. It's not great to see the dashboard this way. I might switch to this guy. So then we can learn a little bit more about the dashboard. Let's see. Can I do that?
Speaking of the dashboard, I've dropped some links in the chat. So we have like a 20-minute video, which is like an introduction walkthrough to like what all the bits of the dashboard mean. It's a super helpful video you might like to look at. And there's also like a 6-minute video on the Jupyter Lab extension, which is just like a more convenient way of looking at it if you happen to be using Jupyter Lab.
Yeah.
So, yeah.
So for now, because here we probably can see a little bit more. So you might see that over here, we have every separate kind of task that we've done. So these are the ink tasks, the double, the add, the sum, and the colors over here. These are like all the sum tasks, all the add. You see the inks were 18 calls to the inks overall on the dashboard. And we will see a little bit more what these different shades mean as we go on some workflows that actually take a little bit longer, so we can just sort of stop and see. One nice thing about the dashboard is you can actually grab, select, make these things a little bit bigger and zoom in a specific type. So you see this an ink call. We can reset it. You can move back and forth on time on how things were run. So this one was the last one that we did. So if we zoom in on that, you will see that this one are super short, but you keep zooming in, you'll see the colors match. So this ad, the ones that are over here, of course, they're all one of these 10 that were run. So we'll see now a little bit more action on some more like data science kind of workflows, and we'll play around with DataFrames, and then things are going to get nicer on the dashboard. For now, one good practice is if you're switching from notebooks to notebooks, I'll recommend you to close the client. So this will kind of like remove everything that is over here, and we'll move on to something that hopefully it's a little bit more interesting. Sure. Let's try to make this smaller. There we go. Oops, this run. So at the beginning, we talk about data frames, and we sort of saw that example of when we want to use Dask and when we should stick to pandas. And one thing that might happen to you if you work with data frames and pandas in your workday is that sometimes you have this memory errors because the data frame or the data that you have is too big that doesn't fit on your RAM, on the memory. So Dask allows you to be able to run those workflows, and when you don't have enough RAM, it'll take longer, it will take a good amount of time, but at least you will be able to run them instead of having those errors. So Dask data frame is the interface that sort of like mimics the pandas API, And we'll see a couple of examples now as we go. So we'll learn about how to use Dask data frame. One thing to notice is like the Dask data frame model, you can think of it as, this is a small picture, I wish you could see it bigger, but you can think of a Dask data frame as it's composed by smaller pandas data frames. So if you imagine like a big Dask data frame that is sort of chunked into smaller parts, and each of those parts is a pandas data frame. So those chunks are called partitions. So each of those partitions is a pandas data frame. There are many operations supported, like element-wise operations, and then row-wise operations and filters. And there is a big list of everything that is supported on Dask. So everything that is from pandas that is supported in Dask, but not all the things from pandas are supported in Dask. There are certain things that are super hard to make it work in a parallel way, and other ones, like probably there are not enough contributors to just recreate the whole pandas API in parallel. So, but luckily we have a good amount of things that we can do with Dask that are probably part of your workflow on your day-to-day. So let's see some of those. So as we mentioned before, yeah, like you will probably want to use Dask when you have this typical memory error kind of problem with DataFrames. Right now, for the purpose of the tutorial, especially if you're working in Binder, we are working with a small kind of data that still fits in memory, because otherwise things like could take longer. And the purpose of this is to show you and teach you how to use it more than to see. Towards the end, we might see other examples where data gets a little bit bigger, and then we get to use a cluster. So for now, you can run this. This should get some data set up. Quick heads up, if you are in Binder, you will probably see some difference on the results, because the data on Binder has to be smaller than what it can be in my laptop. If you're working on your laptop, you will see the same results that I do. If you're on Binder, you'll see slightly different numbers. It's not that it doesn't work, it's just the data is tiny. So far, nothing Dask related yet, but here is the way that we will use the Dask data frame collection. So as a general rule, we import Dask data frame as DD. The same way that you import pandas as PD, we'll use DD in it. So we're very creative with the name. And let's try to read a CSV file. So the syntax is the same as before. We have Dask read CSV, and we will pass these files. And remember that at the beginning, when I show you in the overview that we have asterisks in the name of the path of the read CSV as here. So what this will do is, if you go and check on, this should be on your local directory, on the directory that you're working on. If you're in Binder, go back and check on data. You will see the folder of New York City flights. And you see that here we have 10 files that are 10 different read CSV. So in Dask, we can load each of these ones, and each of these small pandas data frames will live in the Dask data frame. So that's what the asterisk for, because we're passing sort of like as a wildcard for the year, and then everything that finishes on CSV. So that's what that asterisk is there. And this is how, oops, it just kicked me out. And this is how we will read them all into one big data frame. So we can parse the dates same way that you could parse the dates in pandas, and you can specify the data type. So if we run this, we see now that we sort of have a skeleton of a data frame. So if we do this, you see you have 10 partitions. One partition corresponds to each of the files that we have. And then we have some columns over here that you can see the types. but then there's nothing else going on in here. So we sort of have this structure, but so far nothing has been computed or fully written into memory. So if I want to see the columns, you can check the columns same way that you do in pandas, similar with the types. So far, nothing crazy has happened, and everything is sort of happening on the back. You can check the number of partitions, that's 10. And if you want to visualize how this data frame looks like, for now is, well, it's the computation server. Like we have the 10 different read CSV. Right now, you see that there is nothing happening on the dashboard. This is because by default, Dask data frame is using the single machine scheduler that we talked at the beginning and the thread one. And you can perform certain computations with that. It will use the 8 threads course that I have. But if you were to run in a cluster or you want to see what happens in here, then you will want to create a client. So we'll see now in a second. You will access head the same way. In this case, when we do head, we are sort of triggering a small computation to see these first values. We're not computing the whole data frame, but we're computing like a small portion to be able to see the first 5 rows. So let's see some action on the dashboard, and then let's use the distributed scheduler. So I'm going to request like 4 workers that we said before. So in your local, if you are working in your laptop, by default, this is always the address of the dashboard. So I can just like refresh this one just to make sure it's there. Still having this from before, but nothing different we have done. So if we were working in pandas and we would like to compute, let's say, the maximum of the departure delays, and you have 10 different files, the way that that would look like will be, I will have to do a for loop on every of the files, read every file, compute the maximum, and then aggregate them at the end. So if I have multiple files, I will have to do this in a for loop. We could probably, I mean, you could use Dask Delayed to parallelize this, but luckily, the read CSV function, it's already parallelized for us in Dask DataFrames. So let's see how we would compute the maximum of the departures delay across all the years that we have on our Dask data frame. So as you see, the syntax is very similar. You will grab that column and compute the maximum. Again, because we're in the Dask world, so far we haven't done any computation. So you could see how this look by doing a visualize. This is a little bit tiny. I apologize about that. Maybe if I do, okay, there we go. If we do a little bit bigger, so you could see that here we have every of these read CSVs. So we have 10, it's getting an item from there. And then it has all these other tasks doing like in each of those is getting in each of those columns is getting like the maximum of the chunk and is reporting those and then is summing them all. And well, not summing them, aggregating those backs and then computing what is there. So if we compute this, we can get, I wonder why this didn't show it here. Maybe it was too fast. Let's try computer again. This should have, there we go. So you see now we have these tags that are the get item, and then over here, the series mac chunk. And in 1 second or 1.5 seconds, we were able to get that maximum over all those files. I'm not sure how long it takes in pandas, but I'm pretty sure it'll take a little bit longer to go over all those files and compute. So let's do some more pandas-like computations that we were interested in on checking when we see this data. So for example, one thing that we could do is there is this column called cancel and that it's a Boolean, right? Like if we see back on, oops, I apologize about that. We see in the head, if we take a look at the column cancel, where is it? Over here. So cancel will tell us false or true if the word or not cancel. So one interesting question would be, how many canceled flights were, or non-canceled flights were. So if you want to check the cancel ones, you just don't put this curly thing in the front. But if you want to know how many were not canceled, you access those this way. You can sum them and then compute. Because it's the Boolean, will be summing like zeros or ones, depending on whether it's true or false. So the non-cancels will like count in this computation. So if we do a compute of this, you'll see some things happening over here. And we got that computation pretty fast. Another interesting operation that it's a common on pretty much any data analysis kind of workflow is tend to want to group by things. So one thing that we could check on this data is, let's see what are the total of non-canceled flights taken by airport. So I want to see how many flights actually depart by airport. We can, so if you see here, we have the non-cancel ones. So we grab the non-cancels from the data frame. So this is sort of some filtering. And we group by them by origin. And we count the origin of each one of this. So I apologize that I guess because of the size of the font, we cannot see the whole computation here, but always at the end, if you want to have the numbers, you will trigger the compute. So if we run this, we'll see some action in there. Another option could be is that we could actually group by the origin and then see what's the average departure delay and then compute. So these are like different examples of computations that you can do. Here they all run like quite fast. So it's not too much that we could see on the dashboard. But one interesting thing is, like, as we saw before, here you have on the top left of the dashboard, this byte stores. This is the total byte stores per autograph cluster. So if you sum all the worker ones, these 4 workers, the total will be over here. So if you see here, I don't have a color or anything. Okay, annotate here. If you see over here, we have 0 and 500 megabytes. So 500 megabytes times 4 is about 2 gigs, which is about what we have in here. So let's say, I just keep that for future reference. Oops. Can I close this? Okay. So here are more examples. Like you can do multiple things with Dask DataFrames. Like what day of the week has the worst average departure delays, and we can compute those by doing a group by day of the week, and then computing the min, and then getting the index max. So you do that, just compute, and then you'll see more actions and different kind of progress. One performance tip is, like, as you notice, we did in every of these steps, we're like actually doing operations that we already did. So sometimes it's like, if you have intermediate steps that you can sort of like save that step to a point or reuse it, then that's a good practice. So for example, if we want to compute, let's say, the mean and standard deviation for the departure delayed of all the non-canceled flights, since Dask operations are lazy, what we call got lazy that when we see all this, like the task graphs first, those aren't the final results until we compute them. So if there is an intermediate result that we can reuse, we want to make use of those. So one way of computing things is what we've been doing up to like now. It's like you have the non-cancels, and then we will compute the mean and the standard deviation. So far here, every time that we do this, we will be actually reading the CSV file. So when we do this, there's not too much going on. But if you see here, this non-cancel, it's actually used over here, So if we do this, we will be actually calling that like sort of twice per thing. So that took like about 3.5 seconds. Now let's see what happens. We try to do the mean delay and the standard delay. So these computations at sort of the same time on one compute call. So that way we could reuse this, that it's part of both the mean delay and the standard delay. So one way of doing this is with the Dask compute, and you can pass both computations in here. So we do that, and that took less time. So there we go. Here, like we have some more practices, and there's actually like a written explanation of what just happened there. But basically, what's going on is, if we check how the task graph looks, which is very big. Let's see if we can see a little bit. It's going to be very big, but you might see that here that read CSV is only 1. So it's like, and it's reusing this read CSV for both the standard deviation and the mean computation. This is probably not, yeah, it's a little bit of a big graph to take a look at it, but yes, so those are like sort of part of the good practices. If you look into Dask DataFrame good practices and computations that are using the same parts, like in this case, the non-cancelled, then this will be a good way of running them. So far we learned about Dask Delayed, we learned about the different schedulers. We saw a little bit of the dashboard. I'm going to show you now that we will be running some machine learning sort of workflows. Hopefully we'll understand a little bit more what the dashboard is telling us. And then let's see how also we can use Dask with scikit-learn and then Dask in a cluster. So I'm going to close the client now. There are plenty other resources about DataFrame. Pretty sure this is not like, it covers only like 1% of all what Dask can do with DataFrames. But hopefully we'll give you an overview of what you could do. So
are there any questions that people might want to either put in the chat or unmute their mic to ask about DataFrames before we switch to the next notebook?
It's a good call.
Just give everyone a minute to sort of think about things while we get them. I personally really liked the sharing of task graphs. I think that's like packing multiple things into a single compute call is not something that I like do very often. Sometimes I do the same thing in a different way. Yeah, like maybe use the delayed decorator on my own function and apply a few different things to the same chunk or the same partition. But like this is a lot simpler way to do it. So I think maybe that is a thing that I will be doing more of later.
Yeah, I tend to forget about that. It's like I don't see it, and sometimes if your computations don't take too long, then we tend to forget about those things. But I could see why it's useful. So it's basically recycling computations. I like to think it like that way.
The other thing I see people doing is like persisting a small intermediate result. And if like Dask has this method called persist, and if you do that, then it keeps the thing in memory, so it doesn't have to recompute the whole task graph from the bottom up every time. And so like I do actually see that get used a lot if you have some sort of intermediate result that's small, that you like just keep hold of that. Do need to remember this for all this other stuff I'm going to do with it later in lots of places. And that's really effective as well.
Yeah, absolutely. I would strongly recommend for everyone that heavily uses DataFrames to go deeper on the Dask main tutorial that is posted at the beginning, and then read the documentation. As Genevieve mentioned, there's this like sort of powerful way of keeping things in memory that is called persist, and it's sort of like for intermediate step results. But if things are way too big, those things can blow up your memory. So I didn't introduce that here because we were like using like a small amount of data, and then like there's no point of doing that. But if you have, if you work a lot with DataFrames, I would strongly recommend you to follow, go and read the good practices about DataFrames and go over the tutorial material where there's plenty of explanation in there. And if you still have questions, feel free to post on the discourse or on the Slack. And there are plenty of probably persist questions on Stack Overflow too. But moving on and seeing, are there any other questions?
There are no other questions about the data frame, so I think, yeah.
All right, so we'll get into the machine learning part. So this is the last sort of notebook that we're going to go over. If you are on Binder, there are a couple things that might not run well and might potentially crash, just because it's it can get a little bit heavy on the side, on the amount of the data. But a little bit of we will do a little bit of a overview of scikit-learn in case that you're not familiarized with how scikit-learn works, and then we will see how within the scikit-learn world we can use Dask as a backend to make things run in parallel. So this part of the tutorial is sort of like a short part of the machine learning tutorial part of the Dask tutorial, the main Dask tutorial. And it's just because it was so well written, so we just readapted and make it a little bit shorter. But in general, like in machine learning, we will have sort of more or less two kind of problems. I'm going to make this bigger until we use the dashboard. What we'll call like CPU bound problems, where data fits in RAM, but your computations take long. So things that we repeat a lot and we do a lot, but they still fit in memory. So one example of that on the machine learning world is when we have many combinations of hyperparameters and we want to run, let's say, a grid search or multiple things that go over and over multiple combinations of the parameters, but it's running the same workflow with different numbers. And then the other kind of problems that we have are what we call memory bound problems, where the data is way too big and it doesn't fit in RAM. And sampling is not an option. Not always you can sample your data and do your analysis or your things. Quick disclaimer here, I am not a data scientist or machine learning expert. So if you are, I apologize if I get something wrong. Hopefully this example will be simple enough that we can all understand when we could use it and when we might be able to use Dask to make things better. So this is a similar plot that the one that we saw earlier. So one thing to notice, and more or less on the machine learning world, is some examples of compute bound problems are grid search or random forest or cross validation score. So in these cases, is some cases that we will actually want to use Dask because we're just running one thing over and over again. So if we can run them in parallel, things will go faster. And then again, if your workflow lives somewhere in that doesn't fit in RAM and is not on the bottom left corner, then we'll probably be able to use Dask. So seeing that dot over there, that stay there, well, we'll leave it there. So for memories that fit for memories, for problems that fit in memory, just use scikit-learn. It's or your favorite machine learning library. When things fit in memory, scikit-learn is really, really, really well optimized, and you probably don't want to mess around. Now, if the models get super large, then you can use Dask-ML job-lib, and we'll see some examples of that. And for large data sets, there are Dask-ML estimators. So this is sort of like versions of certain parts of scikit-learn and machine learning, different machine learning estimators that are optimized to use with Dask. So super quick and sort of like 5-minute scikit-learn lesson is, in general, your workflow will probably look something like this. You will load some data. In this case, we will generate it, but you usually will load some data, import some scikit-learn module for the machine learning algorithm you want to use. You will create an estimator, you will fit your data, and then you will inspect the learn attributes and check the accuracy of your model. This is like a super vague generalization of how the workflows will look like, but one consistent thing is you will have to instantiate an estimator. So let's say whether you're doing linear regression, random forest, or something like that, then you will have like that. There are multiple hyperparameters. So we'll usually kind of try to tweak some of those and then see which one is better than the other. And then you will call the estimator to fit your data, to train the estimator, and then you will inspect the attributes and make some prediction over there. Here, like X is an array of features variables what you're using to predict, and Y is an array of target variables what you're trying to predict. So let's see some examples. So here we are going to generate some data. Scikit-learn has some data sets, and in this case, we're going to make some generate some data to make a classification. So we import scikit-learn, and we get X and Y, and we'll see what these X and Y's are. But X in this case is the sample matrix or design matrix, and usually has n samples by n features. So you will have multiple samples, so usually those are the rows, and then multiple features like imagine that this could be samples is number of persons or number of people, and then features could be height, weight, color of hair, color of eyes, etc. And as it says, a feature is also called an attribute. So it's something that you sort of can measure a phenomenon that you're trying to analyze. And Y are the target values, which are real numbers for regression tasks or integers for classifications. So you could say, for example, Y could be whether the person is, I don't know, taller than 5 foot, yes or no, and something like, or 1 or 0 depends on, in the case of using integers. There are like, for unsupervised learning, Y does not need to be specified. We're not gonna get that much into those details, but that's sort of like, in general, Y is usually a 1D array where I is the entry that corresponds to the target of the ith sample or the row that you're of the person, let's say, for the example that we just gave. So just to take a look at how this data looks like. So if we take the first 8 components, so you'll see that this is like an 8x4 matrix. So it's 8 entries, so 8 samples. And we have 4 features, so we have 4 columns. And then Y will just be like a 1D array that has zeros and ones. In this particular case, I don't think they mean anything. They're just numbers in here. And we will be fitting a support vector classifier. I'm not going to get into the details what this does. You can read about what support vector classifiers are. We just want to see how we can make things faster. So in this case, the syntax will usually go, we create the estimator and then we fit the data. So here, nothing big happened. And then we just get we can inspect the features that were learned. And we have these values, and you can score or get a score and to see the accuracy of the model. So there are multiple ways of checking accuracy and scoring models. We won't get into that, but that's one way of going about a problem. Now, in this case, we didn't explore many different parameters. We just set up this random state to 0. But one way that we could do is try to learn what are the best hyperparameters while training. So one way of doing this is with grid search. And as the name implies, this sort of does by brute force, try different parameters, and then it see which one is better. So the way that we will do this with scikit-learn is we'll import grid search. And here you'll have, so this is our estimator. And then we have this param grid that sort of defines the things that we want to try. So we want C, which I don't recall what C means, but it's some parameter for SVC, and then the kernels. And if we want to try these 4 different combinations, so it's actually more than 4. So it's 4 different combinations. We'll do the grid search. So the way that this is pure scikit-learn so far, and it will start doing some stuff and feeding the model, and then it will tell us at the end, we can check which one are the best parameters and which one had the best score. So if you think about this, each of these combinations could be run in parallel. There's no need to actually wait for one or the other one. So if we check here, it says, well, if you use C equals 10 and then this kernel, then you get, this is the best score. So that's a good thing. So let's see how can we use Dask, or how can we run things in a way that that will tell us, that will parallelize this. So when you have a compute-bound problem, the single machine parallelism, so working on the single machine, it can be done with job length. And this will use, by default, what's it's like a sort of Python way of parallelizing things. And it will look like something like this in your laptop. So you have the training data, and then it will have all the different possible combinations that you're trying to do. And then at the end, we'll choose the best parameter. So when you're using joblib, like one way of triggering this like parallel computations is by passing this njobs keywords equals to -1. So specifying to -1 means that it will run the maximum possible number of tasks in parallel. So if we do that, let's see what happens. So now this should run more or less faster than what it ran before. So it says before it took, how long it took? 14 seconds. So let's see how long it takes now. Took 8 seconds. So roughly half the time. Now, we didn't see sort of what happened here, and we didn't have much control on what resources was using it, but we could use scikit-learn and joblib with a Dask backend. So one way of doing this is we could actually also use the dashboard and see what's happening. So if we create a client, as we did before, so now I'm going to, so this guy Should be now clean. We get the dashboard. We have our workers, and we could actually, let's see if we can do a param grid that is a little bit bigger than what it was before. So we have now different values for C, different kernels, and this shrinking parameter doing something different. So far here, we just set some things. We haven't run anything yet. Now, how can we use Dask as a backend for joblib? So we import joblib, and we use it as a context manager. So we tell with joblib parallel backend, and then we pass Dask. Here is the data. And then we want it to run the grid search fit. So let's see how this is in action in the dashboard. So you'll see now a couple of things going on. One thing I wanted to point out in the dashboard, as things go, you see that there is this gray line on the progress. So that means the amount of tasks that are ready to run, but they haven't run yet. And then we have the color progress bar in here. Those are, if the color is full, those are the tasks that have run, but they're still in memory. We'll see that those bars change along the way. So this run in 34 seconds. So now we run all these multiple combinations in 34 seconds. So what happened here is Dask-ML developers work a lot with scikit-learn and joblib to implement Dask parallel backends. So internally, scikit-learn now talks to joblib, and joblib talks to Dask, and Dask is handling the things in parallel. So in this syntax-wise, you see like there's nothing that has changed too much. If you work with scikit-learn, these things are familiar to you. Probably the newer thing might be using the Dask as a backend. So now we can see what were the best parameters and the grid search, and now it's telling me that, oh, C10, still this kernel, but just shrinking through. Another kind of problem that we have is the memory bound problems. So one example could be, let's create some data and see how this like memory bound problem will actually have a better solution in Dask. So one thing to keep in mind is we will be using a Dask-ML estimator, which is a different version than the one that is on scikit-learn. So it's meant to run in parallel. So we'll make a small random data set locally using scikit-learn. This will create some blobs, has some centers and stuff, and we'll make this part of the data is small, but we will make it actually bigger. If you're not in Binder and you have time or you're playing around after the tutorial, you could make this data super big, up to like 200 samples per block. This will run in a machine with 16 gigabytes of RAM in about 10 minutes. For the sake of time, we will do something smaller. I will use 60,000 here. If you're on Binder, use something like 10,000. So we'll create this, and this is a big array that has some information over here. We'll see it's a 4.5 gigs of data of array that every chunk has about 10 megabytes. And this is telling me a little bit of information of like how many tasks will run, how many chunks do we have, and the shape. So I think it's what, 30 million? 30 million by 20. So if we try to solve this without that, it will probably blow up, will take a long time. So we will do some k-means. So we'll do from Dask-ML cluster imports k-means. And we have, will be our model. And then let's try to fit it. This will take about, I think it's 2 minutes to make things. But the one thing I wanted to notice here is that you see that now we have the gray darker gray, which are the tasks that are ready to run but haven't run. The ones, then you have this sort of color or full color on the dashboard. Those are the tasks that have run, they're still in memory. And then you have this transparent, in the progress bars here, this sort of like more transparent bar. Those are the tasks that have run and have been released from memory. Here in the left, you can see also how many tasks are processing. So these are each of the workers. So task processing, we have 4 workers and everyone has like 2 threads. And you can see here that, okay, 250 tasks, 400, and it's going up and down. Here's some sort of information about the memory. And over in the task stream, like each of these little rectangles are individual tasks that are running. And the colors, so for example, all the drinks, the greens are the ones that are here. Anem, aggregation, and those have a long name that in the task graph means something. So while this run, if you have any questions about the dashboard, this might be a great time to ask them. This should take probably maybe 1 more minute. And that. Does anyone have any questions about the dashboard?
Naty, just to double check that I heard you correctly.
Yeah.
You said the dark colors are tasks that are currently running and also still in memory. Is that right?
That finish, but that are still
okay.
in memory.
Okay,
yes.
Perfect.
And
thanks.
the light one is they finish and then they were released
Great.
from memory. I don't know if anyone noticed that there was some red going on at some point. It will happen again, probably. We'll see more red in the next one. There's certain colors that are related to specific things. So red is whenever we're transferring data from workers to workers. If you see this orange over here, those are sometimes that is spelling to disk or transferring to disk. I can't quite remember. And if you see a lot of white in there's some part that is white, that means that the workers are not doing anything. And if you see black, that means that the tasks have erred. So they were erred, they didn't run, things have gone bad, probably. So you see here, we have a lot of white. So in this part, the workers are not doing anything. For some reason, this is taking longer than what I thought. But in the meantime, I can introduce like, if you see right now, we are like running this like 60,000 kind of like sample. Okay, 3 minutes and 28 seconds. This took less time earlier. But one thing that can happen is, okay, now your data got way, way, way bigger. And this is the last thing we see. But things can get super big, or things can take a long time to compute, and you don't have access to more physical machines. So one way that you could go around that is using some cloud provider that will set up a cluster for you. This is sort of like me taking a little bit of I work at Coil, so I will show you how to do this. It's super simple Coil, but just want you to be aware there are other cloud providers that you could use, and they're also, all of them are listed on the Dask tutorials. What I like about Coil, and this is not necessarily me working at Coil, I used it a little bit before, is all the work that you have to do to set up a cluster on the cloud is taken away, and then Coil is taking care of that. So for example, any one of you can try this now. If you created a Coil account, you have some free credits at the beginning of every month. They'll sort of reset. So you have some credits to play around. I think it's 1,000 credits that you get, or 100 credits. I don't remember exactly that you get per month. But to show you how simple it is to create a cluster on the cloud, you will import Coil And now instead of creating a local cluster, you will create a cluster in the cloud. So I will be requesting 10 workers. And in this case, I am passing the software environment that I have created. If you're interested in setting up your own software environment, there is plenty of documentation how to do that. But I just wanted to show you how you will create a cluster in a simple way. So here, I will run just that cell, and this will take a couple of minutes. But in here, you see that this is spawning up a cluster on AWS. And I'm requesting like 10 workers. And probably each of those might have 2 threads. And by default, I think it has 4 gigs of memory each worker. So we'll see now as soon as it runs. This might take 2 or 3 minutes. If you have any questions, this could be a good time also to ask more questions about what we've done so far, how to look things at the dashboard, what are other plots on the dashboard. I did not mention, but in the dashboard, if you check in more, there are plenty of other plots over here that you could take a look. One thing, we have the worker stuff. So this sort of like give us information about how each worker is doing. You have, this is the task stream and the task how it runs. There is this graph that we haven't seen, but I'll show you how, what does this look like in the next, when we started.
There is one question somebody has, which is what happens if you forget to close the client at the end of, doing your work?
That's a good question, because actually I didn't close it now. When you shut down let's say if you restart the notebook, it will restart the client, but it will actually close it. I mean, there's, if you are, yeah, I mean, nothing bad will happen. If that's a question. If something that sometimes happens to me is I forgot to close a client and then I start to open a new one. So you will get a warning that says, hey, you already have a client running.
Yeah,
and
you're
the
using
dashboard
this
link
for
is this.
what's going on? Yeah.
So
I'm
it
very
will,
bad about
it will tell you.
remembering. Yeah, I always forget to close things, and I see those sorts of things happen a lot. So like nothing super bad ever happens, but like quite often it'll be like, I thought you were using that port already, and I've switched the dashboard to use a different one. It's at a different link.
Yeah. So it will give you a different link, or it will tell you. It's a very informative red thing.
Yeah, but nothing.
We could actually force it to happen. But you see here, I'm already getting some workers. This is a little bit slow for some reason. It's now giving me, okay, 3 out of 10. So I could have started like probably getting this, but the competition would take a little bit longer. Okay, we got 5. Come on, give me all of them. For some reason, it's taking longer than it usually takes. But one thing that I like this is like, it's sort of, I don't have to set things up. It's all taken care of on the back. And now if I create a client, so in this case, it won't give me that red error because this client and this dashboard, it's on the cloud and it's not on my local machine. So now we can access this dashboard, which you will see that it has 10 workers. So if you count here on the back, on the left side, and we can actually inspect how this cluster looks like. So I have 20 workers, 20 threads, and I have a bunch of memory. I have 75 gigs of memory. And if I think every worker has 8 gigs of memory, this is a little bit kind of blow up, but if I make it a little smaller, okay, there we go. So you can see how it looks like, and it has some more information. But in general, usually you get those things. So one thing is, if we do now the same operation that we did before with 60,000, but now we do it with 200,000. So I'm making something bigger because I'm trying to use the resources I have. And this is something that could happen to you. This should be faster. Like if I run it on my laptop, I run this on my laptop. It took about 10 to 15 minutes. Here we see, because I have the memory, I have 75 gigs of memory. Here we can use that persist sort of like tool that Genevieve mentioned before, because it's keeping it in memory. If you have that memory, it will make this computation run a little bit faster. If you don't have that memory, you should not do that step, but things will still run, which in my laptop did, and it ran in 10 minutes. So let's see how long it takes now to run this. To think, okay, things are happening. Now we see how things are moving, and the memory is filling up, as you see over here. And now you see that bunch of red. See, like it says transfer any. It's transferring things to the workers. I probably using more workers than what I should because it's transferring a lot. And you see some sort of like delay in here, but it's running all the, I think this is all the red that I was telling you about. This is part of how things are working on training this model. Is probably not super optimized. But yeah, here is like a good example where you see all this red transferring and then all the colors of things going on. And that's all what I have to show you. We'll let this finish. It probably finish in a few minutes. If along the way you have questions, then I know that this is a lot of information. The learning curve for that, it could be a little bit steep. If you have any questions, feel free to either, you could post an issue on the GitHub tutorial material. I would encourage, if it's a Dask question, to use the discourse. You can link to that tutorial. I'll be there, and then many other people will be monitoring. We'll all be familiarized with that. I think I have, yep. I was probably put the link on the, it will be, I can find it now. But the link of the discourse.
Sure, I can do that.
Yeah, I think I cannot see the chat, but okay.
I think
then
that's a bit hard to do while you're screen sharing. Yeah.
Yeah.
I'll post it.
Well, yeah, I'll remove out now the screen sharing, but as you saw now, it took us to run like pretty much 3 to 4 times the data that we had before. Now it took 2 minutes compared to before that a fourth of the data took 3 minutes. So those are like the advantages of like running on the cloud. If you're interested on trying code and doing more things with that, or Dask clusters in general, then there's information in there. But yeah, I hope you all learn a little bit more. I know there might be a lot of questions, or questions that might pop up tomorrow. If we have any more questions, I don't want to take longer, because probably it's about 2 hours now. But yeah, feel free to ask any questions. Any suggestions that you have, feel free to post them like on the GitHub issues. If you think that there's something we could improve, or something that you think, hey, I didn't get this, and then we can make this better, we're always happy to improve it. I will stop sharing so I can read the chat in case there is something. There we go. But yeah, thank you all for staying, and I hope you enjoyed the ride. I probably talked way too much, and I might have confused more than what I explained, but hopefully I was able to make some things clearer.
Yeah, it was great. Thanks for running it.
Of course, thanks for taking care of the chat and then helping out there. Someone says, how can we get the recording? I do believe that probably Neha might can answer that question.
Yeah, we should have it up on the Women Who Code YouTube channel like within the week, or definitely under 10 days. So
yeah,
I can post the link on the meetup chat section, or if you guys are on the Women Who Code DC Slack as well, we can post it there as well.
Yeah, I did recently run a similar version of this tutorial and it's on YouTube. It's actually the same tutorial, but it was the first one. I'll post the link in there. And I know that we will run this tutorial again live on YouTube I think in December. The idea is to try to make it this more frequent, so then we can just get more people exposed to that. The one on YouTube will have the call background. That's part of the work. But in general, we're trying to, I guess, and then in this I speak more for the Dask community in general, probably Genevieve, I know that you're giving a tutorial in probably 1 week, and there's always some sort of tutorial going on.
Yeah, and Nat's materials link to the official Dask tutorial, which is a much longer sort of 4-hour thing with several other topics that we didn't discuss today. But that actually has a tutorial recording available on YouTube as well at the Sci-Fi 2020 conference. If you're the kind of person that finds video recordings helpful, you can look at that, but you might also do well to skip around to just the section or the notebook that you care about, because it is 4 hours long.
Yeah, I think, there are multiple versions of that tutorial too. I think I will post
it a few times.
So the Sci-Fi,
I think 2020 was the most recent one.
Yeah, that's over there. But if you're also interested, I know that NVIDIA has a couple of tutorials that they also do Dask and GPUs, or some people, or some of the NVIDIA folks. There's plenty of material there to go around. And
do Coiled have GPUs available, or is that still a bit of an experimental kind of feature?
Yeah, there are GPUs available on AWS backend, and I believe that on GCP is getting there. On the AWS, there are GPUs working, but currently you get 1 GPU per worker. So I know that in some AWS instances, you can get more than 1 GPU per worker. Currently, it's only enabled 1 GPU per worker. So in Coil, you can ask the end workers are the kind of sort of the machines, and those you can have CPU workers and GPU workers. So you can ask for multiple CPU workers, but GPU workers is only 1 per end worker of Coil worker. Let's put it that way. I know that there's some sort of material going on in progress to try to get some more examples out, but I think they're still testing it out. Hopefully soon there will be some things out.
Cool.
If we have more questions, have 1-2 minutes, and if not, I will let everyone go. It's probably late. Somehow late for some people, maybe. But
thanks everyone for coming, and thank you so much, Naty and Genevieve, for leading the whole thing. It was very informational. I feel so much better at this now. So thanks so much.
Good. Of course, and then happy if anyone is on the Women Who Code DC Slack. Feel free to ask any questions about this on the Python channel too. I'll be there. So happy to take some questions there too. Oh, that being said, thank you all